Hi, welcome to another episode of Learning Statistics for Engineers. And this is still under the topic probability distributions of discrete variables. In the previous two videos, we discussed about how to construct the probability distribution function of x and how to solve for the mean, variance, and standard deviation of the probability distribution. This time, we're going to discuss a very important concept, which is related or relative to probability distributions for discrete variables. The empirical rule tells us that or what to expect concerning the probability distribution and its relationship to mean and standard deviation for a probability distribution that is mound-shaped or normally distributed. That's what we discussed during the computation of the mean, variance, and standard deviation. It was assumed that the distribution was normally distributed or was normally distributed. But what about probability distributions that are not mound-shaped or not normally distributed, or the the distribution is unknown if it's normally or not normally distributed? A result proved by Chebyshev answered the questions for probability distribution of any shape. Any shape. That is why we have the Chebyshev's theorem. It says that if we go at least k standard deviations from the mean, then we will find at most 1 over k squared of the probability distribution. Thus, if we go at least 2 standard deviation, if k is 2, from the mean, it will give us, or there will be at most 25% of the distribution, or at least 75%. If we go 3 standard deviations from the mean, there will be at most 11%, or 1 over 9 of the distribution, or at least 89%. And if we go 4 and 5, this will be the result. And so, let us try to prove through an example that Chebyshev's theorem is indeed correct. Let us have this one. This is a probability distribution function of a die or two dice that are rolled, and let be the variable x the sum of the numbers or the faces of the dice when it comes to rest. So we have the sum could be 2 until 12, right? So computing for, we will also use the cumulative probability distribution function. So solving for the mean and the standard deviation of this probability distribution, we have here the mean is 7 and the standard deviation is 2.42. Now, let us show that there is at least 75% of the probability distribution within 2q of u, or 2 mean or 2 standard deviations from the mean. So we have our k is 2. Now, if our k is 2, mean minus, so we have here mean, which is 7, minus 2 times the standard deviation, it will give us approximately 2.2. And if it is 2 plus 2q, or 2 standard deviations above the mean, it will give us 7 plus 2 times the standard deviation. Not q, standard deviation. It will give us 11.8. Approximately, at least 75% of the probability distribution is between 2 and 11.8 or 12. So, all here, we will add here, meaning F3 to, P of 3 to P of 11 will be added. So, adding them all equals, or sum of, let us have sum of P of 3 until P of 11. Showing there, it's 0.945 or 94.5%. And it answers to the assumption that at least, or the Chebyshev theorem, that if we go to here, our k is 2, at least 2 deviations from the mean, there will be at least 75%. So at least 75%. 94.5% is more than 75%. All right. Next, let's show that if we go 3 standard deviations from the mean, there will be at least 89% of the distribution. So our k is 3, the same thing. So equals the mean minus 3 times the standard deviation. If k is 2, 2 from the mean is negative, minus, and plus. So we have mean plus 2 times the standard deviation, and mean minus 2 from the standard deviation. The same with 3. So approximately this is point or negative 0.25. What is the plus 3q? So equals mean plus 3 times standard deviation. I'm sorry. Okay. 3 times the standard deviation. And then enter. So it should be between um negative zero point 0.2. We don't have negative zero point 0.2 as x here. So it's obviously we'll start with 2 and then until p of 12. We don't have p of 12. So it means everything will be added. So using the cumulative probability distribution of x, we have 100%. So at least 1.0 or 100% of the probability distribution is between 3 from the mean. All right, 100% is greater than 89%, so it answers to the Chebyshev theorem of at least 89% of the distribution. Now let's apply the theorem to an example or an application. I have here a word problem. Let me bring here. Okay. Example, the temperature associated with an industrial process has an unknown distribution. Okay, the distribution is not known if it's normally or not normally distributed. However, based on sampling, the approximate mean is known to be 25.3 degrees Celsius and the standard deviation is known to be 2.1 degrees Celsius. So we have the mean and the standard deviation. Find the probability of the temperature if we go 2 and 5 from the mean. So our k is 2 and 5. So I prepared a table here. So the mean is 25.3 and the standard deviation is 2.1. So what if our k is 2 and our k is 5? So I have here computed if k is 2 at least or at most 25% or at least 75%. And if k is 5, at most 4% or at least 96%. All right. So u minus k times the standard deviation, or the mean minus the k times the standard deviation, and mean minus k times the standard deviation. So it will arrive here. All right. So this will be the answer. So this refers to the temperature, meaning how do we explain the result? It means applying the Chebyshev's theorem, at least 75% of the time 75% of the time, the temperature will be between 21.1 degrees Celsius and 29.5 degrees Celsius. At least 75% of the time. And at least 96% of the time, the temperature is between 14.8 degrees Celsius and, sorry, this is wrong. Okay, let me check. So this is equal to the mean plus the k, which is 5, times the standard deviation, which is 2.1. So 35.8. So going back, this means at least 96% of the time, the temperature is between 14.8 degrees Celsius and 35.8 degrees Celsius. This is an application of Chebyshev's theorem. All right, I hope you are learning, and I'll see you in the next lesson video. Have a nice day.